Welcome to this exciting discussion on the future of medical AI. Today, we explore how cutting-edge vision language models, or VLMs, are revolutionizing the field of medical imaging and text analysis. With rapid advancements in artificial intelligence, we are witnessing a seamless integration of visual and textual data, bridging gaps in diagnostics and medical research. In this session, we will uncover how these AI-driven models interpret medical images, generate reports, and assist healthcare professionals in making more accurate diagnoses. Stay with us as we dive deep into the world of AI-powered diagnostics, where machine learning meets human expertise to create a more efficient and precise healthcare system. Let's get started. Now, let's dive into the introduction to vision language models in medical imaging. What exactly are vision language models, or VLMs? These are advanced AI systems designed to interpret medical images and generate accurate descriptions. Key capabilities: they can automatically generate detailed image captions and descriptions, making medical reports more efficient. They summarize videos and visual information in medical documents, helping healthcare professionals extract critical insights. By merging computer vision and natural language processing, NLP, they empower machines to understand, interpret, and generate both images and text. Why does this matter? In medical imaging, this technology plays a crucial role in bridging the gap between visual and linguistic data, enhancing diagnostics, streamlining workflows, and supporting doctors with AI-powered insights. As we move forward, we'll explore how VLMs are reshaping healthcare, making it smarter and more accessible. Stay tuned! Let's now explore how vision language models process information using the Encoder-decoder framework in medical imaging. How does it work? At the input stage, the model receives both text and image data. These could be medical reports, radiology scans, pathology slides, or clinical notes. Step 1. Encoding. The encoder processes this input, converting it into a meaningful representation using foundation models, sophisticated AI systems trained on vast datasets. Step 2. Decoding. The decoder then interprets this information and generates useful medical outputs, such as automated Q&A helping doctors retrieve precise medical insights, diagnosis assistance supporting clinicians in identifying diseases, information screening filtering relevant patient data for better decision-making, summarization generating concise medical reports from complex information, image analysis enhancing radiology and pathology interpretations, predictive modeling forecasting potential health outcomes based on patient data. Why is this important? By leveraging this advanced AI architecture, medical professionals can make faster, more accurate, and data-driven decisions, ultimately improving patient care. Up next, we'll dive into real-world applications of these models in healthcare. Stay tuned. Now, let's dive into the introduction to vision language models in medical imaging. What exactly are vision language models, or VLMs? These are advanced AI systems designed to interpret medical images and generate accurate descriptions. Key capabilities: they can automatically generate detailed image captions and descriptions, making medical reports more efficient. They summarize videos and visual information in medical documents, helping healthcare professionals extract critical insights. By merging computer vision and natural language processing, NLP, they empower machines to understand, interpret, and generate both images and text. Why does this matter? In medical imaging, this technology plays a crucial role in bridging the gap between visual and linguistic data, enhancing diagnostics, streamlining workflows, and supporting doctors with AI-powered insights. As we move forward, we'll explore how VLMs are reshaping healthcare, making it smarter and more accessible. Stay tuned! Next, let's break down the key concepts of vision language models, VLMs, and how they function in medical imaging. VLMs operate using three main components. Image encoder. This module processes visual data from medical images, such as X-rays, CT scans, and pathology slides. It extracts meaningful features, allowing the AI to identify patterns and anomalies within the image. Text encoder. This component processes textual data, such as radiology reports or doctor's notes. It helps AI understand medical terminology, context, and semantics, ensuring accurate interpretation of both text and images. Multimodal fusion mechanism. This is where the magic happens. It integrates both visual and textual features, allowing AI to perform tasks that require understanding both modalities, such as generating medical summaries based on imaging reports, answering diagnostic questions with AI-assisted insights, enhancing clinical decision-making through multimodal analysis. Why does this matter? By combining vision and language processing, VLMs enhance diagnostic accuracy and improve patient outcomes, helping doctors make faster, data-driven decisions with AI support. Up next, we'll explore how these models are applied in real-world medical scenarios. Stay tuned.
Now let's explore the components of vision language models, VLMs, and understand how they process medical data. VLMs consist of four key components. 1. Image encoder. This component processes visual inputs, such as X-rays, MRIs, and pathology slides. It extracts meaningful features using advanced architectures like convolutional neural networks, CNNs, excellent for detecting patterns and anomalies in medical images. Vision transformers, VITs, leveraging attention mechanisms for more accurate image understanding. 2-dot text encoder transformer-based architectures process medical reports and clinical notes by converting text into dense vector embeddings. This enables AI to capture semantic and syntactic nuances, ensuring accurate text interpretation. 3. Multimodal fusion. This is where the image and text embeddings are combined into a unified representation. Different fusion strategies include early fusion, merging data at the input level, late fusion, processing each modality separately before combining. Cross-attention mechanisms, dynamically integrating information from both sources. 4th, decoder generates textual descriptions based on the fused multimodal representation. Works similarly to sequence-to-sequence models, producing coherent and contextually relevant text outputs, such as image captioning, describing medical images in natural language. Diagnosis explanation, providing AI-generated diagnostic insights. Why is this important? By combining these components, VLMs can analyze complex medical data, generate accurate reports, and assist in clinical decision-making, ultimately improving patient outcomes. Let's take a deeper dive into the components of vision language models, VLMs, and how they function during training. VLMs consist of four core components. 1. Image encoder extracts key visual features from medical images. Uses CNS to detect spatial hierarchies like edges, textures, and complex structures. Vision transformers, VITs, treat images as patch sequences and apply self-attention mechanisms for global pattern recognition. 2. Text encoder converts medical text, like clinical notes and reports, into dense vector embeddings using transformer-based architectures, captures the syntactic and semantic nuances of medical language. 3. Multimodal fusion integrates visual and textual embeddings to create a unified representation. This enables the AI to understand complex relationships between images and text, improving tasks like diagnosis generation and medical image captioning. 4th, decoder generates text-based outputs, such as medical reports, AI-generated summaries, and diagnoses. Functions similarly to a generative language model, ensuring contextually relevant outputs. Objective functions. During training for VLMs to work effectively, they are trained using specific objective functions. Contrastive loss, aligns matching image-text pairs while distancing non-matching ones, helping the AI learn correct associations. Masked language modeling, MLM, similar to how GPT and BERT are trained, this technique masks certain words and trains the model to predict them based on context. Image-text, matching loss, helps AI distinguish between related and unrelated image-text pairs, strengthening its understanding of visual text relationships. Why is this important? By leveraging these components and objective functions, VLMs can improve medical diagnostics, automate reporting, and enhance AI-driven decision-making in healthcare. Up next, we'll explore how these models are being applied in real-world clinical settings. Stay tuned. Welcome to this section on the architecture of text encoder and image encoder. This slide illustrates how vision language models process text and images together to perform classification and zero-shot prediction. On the left, we see a dataset classifier being created using label text. The text is transformed into meaningful representations by the text encoder, which captures semantic information from the input. At the bottom, the image encoder processes visual data and converts it into an embedding space. By comparing the image and text embeddings, the model can make accurate predictions, even for unseen classes. This is known as zero-shot learning. This technique is particularly useful in medical imaging, where AI models can classify new types of medical conditions without needing labeled examples for every possible case. Next, we'll explore how these encoders integrate into a full vision language model. Let's now explore the architecture of contrastive pre-training, which is a foundational approach for aligning visual and textual representations in multimodal models. On the left side of the slide, we have two input types. First, a text input, in this case, Pepper the Aussie Pup, which is processed by the text encoder. This encoder transforms the text into a numerical representation in a high-dimensional space. Simultaneously, an image of the pup is fed into the image encoder, which performs a similar transformation, encoding the visual content into a comparable vector space. The key objective here is to ensure that matching text-image pairs, like the image of Pepper and its corresponding caption, are mapped closer together in this shared space, while non-matching pairs are pushed further apart. This is achieved through contrastive learning. On the right, we see a matrix that represents the similarity scores between all image text pairs in a batch. Each cell in the matrix contains a score indicating how well a particular image, denoted I, aligns with a particular text, denoted T. For example, I1 paired with T1 ideally has a high similarity score, while I1 with T2 or any mismatched pair should have a lower score. During training, the model is optimized to maximize the similarity of correct pairs, like I1 and T1, while minimizing the similarity of incorrect pairs, such as I1 with T2, and so on. This contrastive objective helps the model learn a robust and generalized alignment between visual and textual modalities. This architecture is fundamental in models like CLIP, enabling powerful zero-shot learning capabilities, where the model can understand and relate text to images without needing task-specific fine-tuning. Welcome to this presentation on the VC-GPT framework. Let's break down how this innovative architecture enhances visual language understanding. Traditionally, image understanding in vision language models relied on object features, as shown on the left side of the slide. An object detector model would first identify individual items, like sea, person, surfboard, and beach, extracting features from each object. This method, referred to here as the old paradigm, is limited because it may miss out on contextual relationships and finer image details. Now, contrast this with the new paradigm, using patch features. Instead of focusing on detected objects, the entire image is divided into patches. Each patch provides a detailed feature representation of that specific region. This patch-wise approach allows the model to better understand spatial and contextual relationships within the image, resulting in more accurate descriptions such as a person holding a surfboard on the beach. These patch features are then passed into a visual encoder that captures the rich visual information and, alongside, a language decoder processes the textual components. On the right side, we have the model prediction module. It consists of multiple layers including self-attention, self-at, and cross-attention, cross-at, mechanisms, where the visual and language modalities interact. The model leverages a self-ensemble module and a cross-modal fusion module to merge single-modal and cross-modal insights, generating logits for final prediction. The key takeaway here is that the VC-GPT framework moves beyond traditional object detection by leveraging patch-based feature extraction, coupled with powerful cross-modal fusion techniques. This leads to more comprehensive understanding and generation of visual language outputs. Now let's take a look at the vanilla framework, which serves as a foundational structure for many vision language models. On the right side of the slide, we have a standard transformer-based architecture that processes visual inputs to generate meaningful language outputs. Starting with the image at the bottom, it is divided into patches and passed through a visual encoder. This encoder extracts feature representations from the image, which are then used as inputs for the language generation process. These visual features are passed into the language decoder, which is structured into multiple layers, each consisting of 3 core components: self-attention, cross-attention, and a feed-forward network. Let's break down these components. Self-attention allows the model to understand dependencies within the generated text, enabling the decoder to refine its understanding of the language context. Cross-attention is where the model integrates visual information. Here, queries from the language decoder attend to the key and value vectors coming from the visual encoder, allowing the model to ground its text generation in the image features. Finally, the feed-forward network processes this integrated information to produce the output prediction. This process is repeated n times through multiple layers, enabling deep integration of visual and textual information. At the top, we see the model prediction, which in this case is the sentence, "A person holding a surfboard on the beach." A key detail here is how the components are initialized. Modules outlined in black are initialized from GPT-2, modules in blue are initialized from CLIP, and modules in pink are randomly initialized. This hybrid initialization helps leverage pre-trained knowledge from both text and vision domains, improving model performance while also enabling efficient training. This vanilla framework represents a strong baseline for visual language tasks, and understanding it sets the stage for more advanced architectures.
The image encoder processes visual data to extract meaningful features. Object detectors identify and localize objects within images, providing region-based embeddings. Convolutional neural networks extract hierarchical visual features from images, capturing patterns from simple edges to complex structures. Vision transformers process images as sequences of patches, capturing global context and relationships. The text encoder processes textual data to understand context and semantics, utilizing architectures like transformers to generate embeddings. Multimodal fusion mechanism integrates visual and textual features to perform tasks requiring both modalities. Early fusion combines visual and textual inputs before deep processing. Intermediate fusion fuses modalities after some independent processing. Late fusion processes modalities independently, allowing specialized processing before integration near the output. The decoder generates the desired output, such as textual descriptions or answers, from the integrated multimodal representation.
Let's now explore an application of VML, or Vision Language Models, in the medical domain, specifically in medical image analysis. This slide illustrates how VML can be used to process and interpret complex medical data, such as brain scans, and generate human-like explanations. Starting from the top left, we have the user input. A clinician, researcher, or patient might ask a question like, "What is this image?" referring to a medical scan, such as the brain image shown here. This input is then passed into the multimodal processing module. Here, the image is analyzed by an image encoder, while the accompanying text, if any, is processed by a text encoder. These encoders work together to understand and align the visual and textual information. Next, we move into model analysis, where the system performs data processing and prediction. This step involves using the combined visual and textual data to generate insights or identify patterns. For example, the system might detect signs of a neurological condition. The output is then delivered as verbal output, where the model generates natural language explanations. In this case, the model correctly identifies and states a Parkinson's patient's brain. Importantly, this system includes a feedback loop. Users can refine their queries or ask follow-up questions, allowing for an interactive and dynamic diagnostic process. This helps users drill down into more specific concerns or verify the model's predictions. Overall, this application highlights the power of vision language models in healthcare, where they can aid in diagnostics, enhance understanding of medical images, and support clinical decision-making with intuitive, explainable outputs. Let's take a look at some key benefits of vision language models, or VML. VML systems are powerful because they can process and understand both visual and textual data together, enabling a wide range of applications. Let's walk through 4 major benefits. First, we have image captioning. This involves generating textual descriptions for images. For instance, given a photo of a person surfing, the model can produce a caption like, "A person holding a surfboard on the beach." Next is visual question answering. Here, the model can answer questions based on image content. For example, if you show the model a brain scan and ask, "What condition does this indicate?" it can respond with a medically relevant explanation, provided it has been trained on such data. Third, we have image text retrieval. This refers to the ability to find relevant images based on textual queries and vice versa. For example, typing "sunset over the mountains" retrieves matching images, or uploading an image helps find similar visuals or related captions. Lastly, multimodal chatbots. These systems engage in conversations that involve both text and images, offering a more natural and flexible user interaction. This is particularly useful in areas like education, healthcare, and customer service, where visual context enhances communication. Overall, VML significantly expands what AI systems can do, making them more versatile, interactive, and useful in real-world applications. Let me know if you'd like to dive into any of these benefits in more detail. Now, let's look at some real-world applications of vision language models, or VML. These models are versatile and can be integrated into a variety of domains. Let's walk through a few key applications. First, visual question answering. This involves answering questions based on visual content. It is particularly useful in educational tools and interactive systems, where users can ask questions about an image and receive informative, accurate responses. For example, students might interact with visual learning aids that respond to their queries in real time. Second, image captioning. VML can generate descriptive text for images, helping with content accessibility and organization. This is especially valuable for visually impaired users or for managing large image databases with automatically generated, searchable captions. Next is text-to-image generation. This application focuses on creating images from textual descriptions. It has significant potential in the design and creative industries, where artists, marketers, and developers can generate visual content by simply describing it in words. And finally, cross-modal retrieval. This means finding images based on text queries and vice versa. It greatly enhances search engine capabilities, making it easier and more intuitive to find relevant visual or textual content across different platforms. Overall, vision language models are driving innovation across education, accessibility, design, and search technologies, making interactions with digital content more seamless and intelligent.
Thank you, and see you in the next video. Thank you for watching. Stay tuned for more insights on AI in healthcare. Don't forget to like, share and subscribe. Have questions or thoughts? Drop them in the comments below. Follow for more AI and medical tech updates.